Hi everyone. Today we will talk about the fatigue life evaluation of welded joint used in a high capacity press using different approach. My name is Buse Yarşılıkal. Outline of our presentation, we will start with the introduction, after that nominal stress method, hotspot method, effective notch method, and finally we will pass our finite element model, which we will indicate in the abacus. So bracket finite element model, and then conclusion with the results. Welded connections are commonly used in construction of heavy machinery equipment. Numerous methods and approaches have been developed in order to evaluate fatigue life of a welded connection systematically. Determination of mean and amplitude values of stress components, as well as selection of appropriate SNN curve, is crucial steps in fatigue evaluation. And you can see in this picture a welded joint of a bracket which is used in a high capacity press, which produced from Repcon. Finite element method is used in order to determine stress state of the structure which is subject to complex loading scenarios. However, it's not always straightforward to determine stress value at weld critical locations such as toe or rod, since there is always a singularity inherent to weld geometry. Standards suggest different approaches in order to eliminate stress singularity and obtain reliable stress value. Nominal stress, structural hotspot stress, and effective notch stress methods are commonly used methods which are described in standards. In this study, a load-carrying welded joint of a high-capacity presses is investigated based on fatigue life evaluation. Different approaches defined in FIKM and Eurocode standard were applied in finite element models in order to determine stress components. SNN curve appropriate for welded connection configuration were determined from standards. Approaches considered in this study were compared based on modeling effort and attained fatigue life. There are basically four different methods to calculate fatigue life of a welded structure, which are nominal stress method, hotspot stress method, effective notch reduce method, linear elastic fracture mechanism. In this study, various analyses were conducted for load-carrying cruciform welding. In this type of welding, the load is applied to discontinuous part and not the continuous part. The load applied to the discontinuous part is transferred throughout the weld to the continuous part and then back throughout to the weld to the other discontinuous part, which you can see in here, cruciform welding part. Continuous plate is here, also discontinuous plate is here. In the nominal stress method, calculation was made according to the International Institute of Welding standard, but plus determined for cruciform joint are given site. You can see here structural detail in here, description for the steel and aluminum material, fat value for the steel and fat value for the aluminum, requirement and remarks is given here. Let's continue with the hotspot stress method. Reference point and different type of meshing given here, which is hotspot type A and hotspot type B, and the fine mesh or finer mesh given here, relatively coarse mesh given here. Also, what's the type A and type B? Type A can be determined as the structural hotspot stress transfer to weld on the plate surface, but while type B can be determined as structural hotspot stress transfer to welded at the plate edge. Also, you can see in this table recommended meshing and extrapolation in the standards, type of model and weld to shells or solid or coarse model, fine model. There is a different approach here. Calculation of structural hotspot stress, type E Fine mesh with element length not more than 0.4 T at the hotspot, and evaluation of nodal stress at two reference points, 0.4 T and 1 T, and linear extrapolation. This is the first equation. Fine mesh as defined in here, evaluation of nodal stress at three reference points, 0.4 T, 0.9 T, and 1.4 T, and quadratic extrapolation given belong to here. This is the second one. Coarse mesh with higher order element having lengths equal to plate thickness at the hotspot. Evaluation of stresses at mid-side point or surface centers respectively, two reference points, 0.5 T and 1.5 T, and linear extrapolation equations are given here. Continue with the effective notch method. The effective notch stress method contains the effect of local yielding. This approach is based on the statistical evaluation of fatigue test result, and the calculated notch stress is determined via the linear elastic calculation. Therefore, the effective notch stress is used only considering the effect of different geometrical properties of the analyzed structure. Plastic deformation could be also taken into account if residual stress due to the welding will be determined and incorporated in the numerical model as well. The stress computed using the detailed model can be directly compared to the S and N curve, which is not specific for the type of joint, for the reason described previously, but present a high level of variability in their shape. So this method assumes an effective weld profile based on the throat thickness and a certain notch radius. You can see in this table recommended mesh size and FAT classes, which are quadratic and linear, and R size. Also in this table, FAT classes for the effective notch stress approach, location, and FAT class value. In this slide, we can see our finite element model, which we run it on the abacus. So in this picture, welded joint of a bracket, which is used a height capacity press produced from Repcon. And here we have a finite element model and mesh geometry. Also, you can see here boundary condition in the simulation. We use the submodel for the analysis for easier and quickly further on. Effective notch model, which is radius 1. 3D model are developed to investigate the effective notch stress approach. The size and the type of applied elements were chosen according to the reference table. You can see the model and the meshed geometry. Result of the case of effective notch model radius 1. Maximum principal stress result shown in here. Also, in this section, Z direction stress result given here for the detail. In here, different section of maximum principal stress result given there for here and here. The stress result from different section along the normalized distance path for the effective notch case. In this graph, maximum principal stress versus normalized distance along path for the different elements which are given here. Also, they match very well. Hotspot stress results, and in this graph, stress megapascal and X device T results, which are total stress, linear extrapolation, and quadratic extrapolation for the path given here. hotspot stress linear extrapolation result and quadratic extrapolation considered with the stress which is recommended FKA. Also structural detail we according to standard belong to here. When we compare it with them, both extrapolation methods show that the hotspots stress below the FET value. However, the quadratic extrapolation predicts slightly higher stress, which you can see here, which might be considered a more conservative estimation. Conclusion, we talk about the different approach for the welded joint height capacity spreads investigated based on fatigue life evaluation. We talk about effective notch stress, hotspot stress method, and then we calculate in the finite element model and discuss further results. For the effective notch method, the results were compared based on the number of elements applied normalized distance along the paths. Thank you for your attention.